And this is particularly relevant to us because of what we've been discussing, namely qubits and Bell states, right? Two-dimensional systems and entangled states. So as I said, this is the setup. Consider a general physical theory. So I think this is where I left off last time. Just check. Yeah, okay. So last time I kind of summarized all the sort of different questions that people were asking around this. But let me jump into the actual test itself now. So imagine you have two labs, A and B, or two parties, Anita and Bharat, and let's say that we consider, so like I said, a general physical theory. So I'm not assuming any quantum mechanics now, right? I'm saying that we are in some world where there is a general physical theory that is operational, right? And let us think of four binary valued observables. P, Q, R, and S. Okay. And let's say that two of these observables will be measured in A's lab, and two of these observables will be measured in B's lab, right? So there is P, which takes values plus minus 1. There is Q, which takes values plus minus 1. And then there is R and S, both of which take values plus minus 1. There are four physical quantities which take exactly one of two values. Of course, there are several such quantities we know. Spin observables are simple example of this. There could be energy states of two-level systems, right? There could be anything, polarization states of light, etc. So we have these four binary valued observables. And now we are going to make some reasonable assumptions. These are assumptions which we think any reasonable physical theory should satisfy. What are these reasonable assumptions? The first one is what is called realism, like I said often. So the idea is that P, Q, R, and S are objective properties of the system. We say systems, and the act of measurement merely reveals their values, right? This goes back to what I think someone asked me in the very initial days of this course about what is the value of the spin of this particle before it enters the Stern-Gerlach setup, right? So there is a school of thought which says that all physical theories must have objective reality, right? Which means that quantities should take on some inherent values, right? That's what our classical intuition tells us, right? Our act of observing the particle is simply to reveal this value of this inherent property. It is not something which, it is not something which is decided at the point of measurement. However, of course, quantum mechanics tells us otherwise. But anyway, let's assume that we are working in a reasonable physical theoretic framework and then see what constraints we get. And so that will become a way to test whether the world behaves this way or whether, it is really quantum mechanical, right? So I don't know if you guys are interested in history and philosophy of science and so on. There's some famous debates between Einstein and several of his collaborators. So one of these commonly quoted phrases here is when Einstein suddenly asks his close friend and collaborator, Abraham Pace, who is also his biographer, he turns to him and says, "Do we believe that the moon exists only when we look at it?" Right? So that's sort of at the heart of this debate. Do physical properties have objective, can we associate objective values with them, right? The second property is what is called locality, right? We assume that physical theories are local. In fact, we assume they are local realistic in general, right? And we will see, of course, that this is going to be violated in what we discuss. So the idea is that A and B are causally disconnected. What happens in A cannot affect what happens in B in any physical way, right? There cannot be, there's no physical connection between A and B within the boundaries of space-time, right? They are in disconnected regions of space-time. So what happens in A cannot really affect B, and what happens in B's lab cannot affect A's lab, which means their measurement choices cannot affect each other, etc. So they're completely, in the language of probability, we will say that these are independent events. A deciding to measure something and A observing something is independent of B deciding to measure something and B observing something, right? That's the assumption, that they're causally disconnected. And so it is possible to assign joint values to P, Q, R, and S simultaneously. This is important, this word. So the idea is that A and B perform their measurements at the same time. That's another way of thinking about it. So this basically says that what we have is a local realistic theory. Okay. Now in this local realistic theory, we are going to put some constraints on the expectation value of some function of these observables. So now we have considered these four observables, P, Q, R, S, and we've said two of them will be measured in A's lab and two of them will be measured in B's lab, right? And of course, A and B share some joint state, okay? It's just a, two particle system, right? There are two particles or two physical systems which are shared in whatever sense by A and B, and there are four quantities they're going to measure, right? So so now let us consider an observable M, which is some function of PQRS. In particular, this is the function we will consider. So this is PR plus QR minus PS plus QS. Right? This is just a product. It's P times R plus Q times R minus P times S plus Q times S. So essentially this is P plus QR plus Q minus PS, right? And since we have said P and Q are binary valued variables, I mean all of them actually, P, Q, R, S are all binary valued variables, but in particular, P and Q are binary valued variables, so they can only take plus minus 1. Then I hope you can see that what are the values, possible values that M can take? Yes? What are the possible values that M can take?
R and plus minus S.
Yes, which is what?
The value that we
Yeah, but all of them are plus minus 1. So what is M? You can exactly say what M is. Exactly. Thank you, Manoj. So M has to be plus minus 2. Right? So think about it. Because PQRS can take only one of two values, so M can be plus minus 2. Now, I see some question in the chat about Bell proving that realism assumption is wrong, etc. Yeah, we'll see what are all the assumptions that get violated, or what are all the assumptions that we are forced to discard. Okay, so now let's assume that this is a probabilistic theory. So let PR of, so I'm going to call this little PQRS, okay, be a joint distribution, is a joint probability distribution over the outcomes PQRS. So what do I mean by this? So first let me say, let P denote the outcome of measuring observable P. Okay. Let Q denote the outcome of measuring observable Q, etc. Right? So also R and S. Okay. So the idea is to show that it is not just that quantum mechanics is a probabilistic theory. You could have had, for example, a probabilistic theory which is still satisfies these assumptions of, local realism. But the idea, Bell's idea essentially was to show that it is not so much just the fact that quantum mechanics is probabilistic. There's something beyond that. It allows for certain kinds of observables and certain kinds of states which violate some of our very strong classical intuitions, right? So little p, q, r, and s will denote the outcomes. It's not so important, but just want to write this formally. So let PR of this PQRS is some function. It's a joint probability distribution over these outcomes PQRS, right? These outcomes can take values plus minus 1, of course. We already said that. So now if you have an underlying probability distribution from which these are taking on values plus or minus 1, one can write down an expectation value, right? We can write down an average. So let us say that expectation of this function M, right? So what I want to now show you is that this puts a constraint on what can be the expectation value of M. And it doesn't matter what this joint probability distribution is. It just must be a well-defined joint probability distribution. Okay? So there is some assumption going into even writing something like this. And that goes back to this assumption of locality and realism. Because these measurements are independent events, they are happening in causally disconnected regions of space-time. So it is possible to write down a joint probability measure over this set of observables, right? So then we can define this expectation value. Well, this expectation value is nothing but, remember, M itself is a function of little p, q, r, and s. It is PR plus QR minus PS plus QS. So this is going to be a sum over these different outcome values. Remember, they all are, plus minus 1. Probability of PQRS, the probability distribution, times the function. And what is that function? It is PR plus QR minus PS plus QS, right? So when I sum over this, I hope it is easy for you to see that because these observables are constrained to be plus minus 1, this expectation is essentially constrained to be less than equal to 2. Okay, in fact, if I take, so of course the expectation of, so I hope everyone sees that, right? So this expectation should be, it doesn't matter what this distribution is, but because this function itself takes on values only plus minus 2, right? This expectation must be bounded from above by 2. So the left-hand side is nothing but expectation of M, which is nothing but expectation of PR plus expectation QR minus expectation PS plus expectation QS, right, should be less than equal to 2. In fact, you can put a lower bound also. What should be the lower bound? -2, indeed. Good. So that's it. But we'll concern ourselves only with the upper bound for now. So sometimes people like to put a modulus and say that it is less than equal to 2, which is also fine. But basically, this expectation lies between +2 and -2, right? So there's nothing great and grand we've done. It's just basic probability theory, right? Very, very basic. But now we are going to show that there exist quantum states. So this, by the way, that's it. So this is the so-called Bell-CHSH inequality. Okay? And it simply says that if I have a local realistic theory, and I have this set of binary valued observables, which are measured on some joint state, right? Then this expectation is constrained to be between plus and -2. So now, what happens in quantum mechanics? The key point is quantum theory allows for states and observables, and this is very important. Okay, you need a certain kind of state and you need a certain set of observables to actually show that quantum theory can violate this inequality. So what are these states and observables? Of course, the state is now going to be one of the Bell states, right? So let the joint state be psi AB be one of the Bell states. In this example, I've said it's beta 1, 1. So actually what you're going to do in your assignment is to work this out for beta 0, 0, right? Just to show you that any of the Bell states will do. And what are the 4 observables we are going to take? Of course, they're going to be some Pauli spin observables, but we are going to, of course, have to construct a specific set of them, right, to see this violation. So the shared state is beta 1, 1, and P, which is now, I have to put little subsystems here, but it doesn't matter. P is basically the sigma Z observable. Q is sigma X. R is minus sigma X minus sigma Z by √2. And S is sigma Z minus sigma X by √2. Okay. So of course, note that we have chosen these 2 observables P and Q such that P and Q do not commute, correct? The commutator of PQ is not 0. What can you say about the commutator of RS? Is it 0 or non-zero?
It's 0.
Why is it 0?
Like there will be a commutator of sigma Z and sigma X plus a commutator of sigma X and sigma Z, and because it is.
Do they come with the same signs?
Yes, and when we add them up,
they don't come with the same signs, no? There is plus sigma X, sigma Z, sigma X. And there is minus sigma X, sigma Z. And minus sigma X, sigma Z is plus sigma Z, sigma X. So I claim, in fact, that this is not 0, but please check. Okay. Watch out for the signs and the order. Right? Okay, so we have basically chosen observables. So these are the local observables, right? And the local observables don't commute, right? So now, what do we have to test? We have to test whether expectation of this observable M, which is now the same thing, it's going to be some of these 4 expectations, PR, QR minus PS plus QS, right? And so quantum mechanically, this is going to be expectation in the state beta 1, 1 of, now what do you mean by saying PR? So remember that when I say PR, here it means P in subsystem A, tensor identity in subsystem B, right? Identity in subsystem A, tensor R in subsystem B. But now, as again, I hope we discuss this when we discuss the Kronecker product. This is the same as PA times identity. I'm sorry, I should put I. P times identity is just P, so this is PA tensor RB, right? So that's what we mean by PR, right? So which is what? Sigma Z tensor minus of sigma Z plus sigma X by root 2, okay? Beta 1, 1. So that's the first term. So yes, I'm going to ask you to start evaluating these terms, so please do so. At least just evaluate the first term for me and tell me what you get, okay? Please evaluate this first expectation value. I'm going to write down all the terms. So it's beta 1, 1. And then QR, which is sigma X tensor again minus of sigma Z plus sigma X by root 2. So this is all mid-sem exam practice. Huh? Please work out what the first term is. I just want you to work out what the first expectation value is. It's minus beta 1, 1. PS, so P is again sigma Z, tensor Z minus X by root 2. Then you have the last term plus beta 1, 1, sigma X tensor sigma Z minus sigma X by root 2. Okay, so let's just evaluate the first term. So this itself has two terms now. So this is beta 1, 1, Z tensor Z. So it's minus Z tensor Z by root 2, right? Minus Z tensor X by root 2. So several ways of doing it. One way is to write down what beta 1, 1 is here, right? So that is 0, 1 minus 1, 0. Act your ZZ on that, see what you get, and take the inner product, right? So has anybody done that already? So this is now 0, 1 minus 1, 0 by root 2. That's what is on the left. And then I have ZZ acting on 0, 1 minus 1, 0. Remember that Z does nothing to 0 and flips the sign of 1, right? So what I get on the right is minus 0, 1 plus 1, 0 by root 2, but then there is an overall 1 over root 2 as well. Keep that in mind. Okay. Then the second term, again has an overall 1 over root 2, 0, 1 minus 1, 0 by root 2. And now I have ZX acting on 0, 1 minus 1, 0. And X is going to flip, right? 0, 1 will give me 0, 0. And ZX on minus 1, 0 will give me plus 1, 1. Okay? So you see the benefit of writing it like this. Basically, this then boils down to the expectation value of, the inner product between two of the Bell states. So what is the second term? Inner product between two of the Bell states?
Zero.
Yeah, the second term will vanish. So what does the first term give you? So I claim that the first term simply finally evaluates to 1 over root 2. Do you get that?
I got 1 over root 2. Yes.
Okay. I'll just give a few more minutes for people to work this out. So if you've done the first term, go ahead and do the second term. Second term becomes xz minus xx. Once again, you should be able to argue that the xz term is not going to contribute, because if you see that its action on one of the Bell states will turn you to one of the other Bell states. And then the xx term is going to flip the 0, 1 to 1, 0 and the 1, 0 to 0, 1. So once again, so what I'm now going to say is, in fact, all the terms every term evaluates to 1 over root 2. Okay, so this is for you guys to check that if I do beta 1 1 sigma x tensor minus of sigma z plus sigma x by root 2 beta 1 1, this is also 1 over root 2. Okay, and then beta 1 1, I have sigma z tensor z minus x. See, it's a set of repeating terms, right? You have zz and zx, and you have to take the expectation value of those two terms. That's all. And they come in various combinations of plus and minus signs, right? So that's all you need to keep track of. So this is for you to check. So then what is that expectation value now? Expectation value of this observable M, which was expectation PA tensor RB plus the second term QA tensor RB minus the third term plus the fourth term What is this? Actually, I think I made a mistake. The third term should actually come with a minus sign. So just note that here I have, yeah, I'll have expectation of ZZ. So if you notice here, the expectation ZZ came with a minus sign, right? And that's what became a plus 1 over root 2. So if this minus sign were not there, then expectation ZZ gives me minus 1 over root 2, right? So the third term alone comes with a minus sign. Please watch out for that. So that's the PASB term, right? So what does this then evaluate to? This basically evaluates to 4 by root 2, which is 2 root 2. Okay. So this, the fact that you have states, we have identified states and observables. So The bottom line is that quantum theory allows for states, namely these kind of entangled states and observables, in particular non-commuting observables. So you see, it boils down to the fact that there is this whole linear algebra structure on which this theory is constructed, right? It's not just the fact that it's a probabilistic theory, it's the fact that the structure, the mathematical structure of states and operators is just completely different from what it is in classical systems, right? So it allows for entangled states, it allows for non-commuting observables, such that we can have this expectation of m to be 2 root 2, which of course violates the bound, right? Violating the so-called Bell-CHSH inequality, which, remember, said that this expectation must be less than or equal to 2, right? So now we have actually a means to test which is the case, right? So if I actually take an entangled state, and if I actually, so the key point, of course, is that one must allow for this entangled state to somehow be shared across two very separate regions of space-time, right? So you have to really be so far apart that this locality assumption becomes quite strong, right? Otherwise, one may argue that, well, you were still in some causally connected region, so maybe you were really not exploring the limits of this inequality, right? So these are called sort of loopholes when you do an experimental test. But if you assume this kind of ideal experimental test where you can take them far enough apart, and then these are local spin observables, right, which we know how to, for example, do in a Bloch sphere. One can do these measurements, right? And one can actually then write down the output statistics, and one can ask, are these statistics such that the expectation value satisfies the Bell-CHSH test, or does it not, right? And of course, now experiments have happened where this violation has been shown concretely. It has been shown in various systems. So I've actually posted a recent, well, relatively recent paper which proves experimentally demonstrates a violation. Meaning it demonstrates something which is beyond 2. Maybe, experimentally you have so many sources of noise and inefficiencies and so on. So you may not hit the 2 root 2. But generally you cross this threshold of 2 by a well enough margin, then you say that you have violated the Bell-CHSH inequality. Okay. So what is CHSH? So this refers to 4 people: Clauser, Holt, Shimony, and Horn, I think. So the inequality that, yeah, it's Horn, I think it's spelled Horn, and I think the order, I've interchanged the 2 H's, the order of the 2 H's, but it doesn't matter. So this particular form of this inequality was written down by these guys in 1969, right? This is what I would say is this is a specific example of a larger class of Bell inequalities. Okay, so the idea that you could write down an inequality based on a local realistic theory, and then you could identify quantum states and observables you're going to violate, right? This whole framework was laid down by John S. Bell. Like I said, he was a particle physicist at CERN. This was the early days of the Large Hadron Collider experiment at CERN. They were building the detectors in the collider at that point, and he dabbled in what is today called quantum foundations in his free time, right? So in his free time, he wrote down this framework where he wrote down sort of set of inequalities. But his, the inequalities he wrote down were not this simple and, this easily testable, but these were converted into this form by these guys. So this is the commonly used test today. For example, this can be used as a test even for entanglement. So if the Chinese claim that they have managed to share a pair of entangled photons from space, then the question you should ask them is, have you done a Bell test? Have you managed to show that this pair of states that you have received in two distant locations actually violate the Bell-CHSH inequality? Right? So this can be used as a test for entanglement. It can be used for verifying entanglement. So as experimenters, this is one of the first tests that you will have to do to show that you have generated entanglement in your lab, right? This can also be used to quantify entanglement. How? Well, this expectation value of 2 root 2 was achieved for the specific case of the Bell states. And remember, we said that the Bell states are maximally entangled based on a kind of entropy definition, the entanglement entropy definition, right? But one could also use a Bell test to check, right? So the expectation is, so it can be used to as an entanglement measure, because for entangled states, so let me put it this way. So for product states, so let me back up a little bit. So it is not as if all quantum states are going to violate the Bell-CHSH test. It's not as if all observables are going to violate the Bell-CHSH test. Okay. So in particular, note that product states will not violate the Bell-CHSH bound. Okay. So that's why this is a test for entanglement. Second, the fact that expectation M is 2 root 2 is in fact the maximal possible violation. And this is question 4 of assignment 2, where you will show that if you assume qubits, for example, then you cannot have a violation which goes beyond 2 root 2. Okay? So this is the maximal possible violation, let me say, for qubits. Okay? If I have a pair of two-dimensional quantum systems, I cannot violate the Bell-CHSH bound beyond 2. But remember, we were only discussing 2 outcome measurements. So even the classical bound of 2 is only for 2 outcome measurements. So quantum mechanically also, we are then constraining, to compare apples and apples. So we are constraining ourselves to systems where the, maximum number of orthogonal states you can construct is 2, right? So if you look at 2-level systems of qubits and compare it with 2 outcome measurements, then the classical upper bound is 2, but the quantum upper bound is 2 root 2. And so what we are saying is that essentially the Bell states achieve maximum violation. So they are the ones that saturate this inequality, right? In the quantum case. So other entangled states will essentially lie between they will have this expectation to be larger than 2. They will be larger than the classical or the local realistic value, but it will be less than 2 root. So depending on what this value is for a particular entangled state, what is the Bell violation that you get, right? What is the extent to which it is greater than 2? That will tell you how entangled the state is, right? So this therefore quantifies this expectation of this M, this particular combination of observables, this quantifies the extent of non-locality. So this is also often called non-locality, right? So people like to use a separate term for this because it does happen sometimes, particularly in higher dimensions, that you have an entanglement measure which tells you that the state is entangled with some number, but its Bell non-locality violation is some other number. So in some sense, you can think of these as two different ways of quantifying entanglement also. The entanglement entropy quantifies entanglement in one way. The Bell violation quantifies non-locality in the state in a different way. Of course, these notions coincide a lot for qubit systems and just 2 qubits. One can think about extending this to multiple qubits, to larger systems, d-dimensional quantum systems, etc. You can write down what should be the classical value first. So there's a big industry around this actually, where people write down newer and newer Bell inequalities and Bell tests, right? So this becomes a way, and this now has become an important tool in quantum cryptography actually. Because suppose somebody gives me a box and says, hey, here is a, so I am Anita and Bharat has given me a box and says, hey, you keep this box and I will, establish a quantum channel with you and I will share entangled states with you. How does someone verify? Or let's say there's a third-party vendor who is selling this box to Anita and Bharat and saying, guys, you can now generate entangled photons and you can start, communicating secretly with these entangled photons. How does anybody verify this? So the Bell test has become a way to check for the presence of entanglement. It is often called a witness, a sort of device-independent witness, and so on, right? So this is an important tool now. What was originally a philosophical question became an important question in quantum foundations and is today an important tool in quantum protocols. Okay. So finally, why do we see this violation, right? What is it about the first theory which was wrong? So like I said, we have made 2 assumptions in this case. One is that of locality and the other is that of realism. So it seems that we have to discard one or both of these assumptions when we discuss quantum mechanics, right? So the fact that you can write down, that these properties of systems are objective properties and they are real in this sense. So this objective reality assumption is inconsistent with quantum theory. So the second point, of course, is that since we now have non-commuting observables, and this is something we already saw when we discussed measurement and sequential Stern-Gerlach setups and all that, you cannot write down a joint probability distribution like this when you have non-commuting observables. So this again is another assumption, and it's a very classical assumption rooted in classical intuition. There is no reason why I cannot write down a joint probability distribution for a set of quote-unquote classical observables on my system, right? But quantum mechanics again allows for observables where this joint probability distribution does not exist, because you cannot simultaneously assign values to these quantities, right? Like the spin X and spin Z and so on. And we already saw manifestations of this when we discussed the Stern-Gerlach setup and all that, right? Okay, so that's pretty much what I had to say. So people still today work on what is called hidden variable models, where they try to see if they can have a non-local hidden variable which can still reproduce all of quantum mechanics and which can reproduce this Bell value of 2√2. I would say it's still a work in progress. I don't think there's been anybody has shown a consistent way to quote unquote complete quantum mechanics. But yeah, I mean, this is a very deep and interesting question, right? Any questions?
Excuse me, ma'am.
Yeah.
So when we were discussing the classical approach, right? And then we
Yeah.
defined the expectation value.
Yeah,
There we were working with a joint probability distribution, right?
correct.
But when we are evaluating the expectation values in the Bell state,
Mhm.
now this is an ensemble expectation that we notion that we use in quantum mechanics. But now you just mentioned a point that since the operators corresponding to the observables are incompatible,
Hmm.
I cannot define that quote unquote classical probability joint distribution.
Correct. Yeah, so what do I mean by that? Indeed, good. So you see, quantum mechanically, I can always define the expectation of something like this, right? Say PA tensor Q RB, right? That's what I was writing down, right? And in fact, if you notice, there is a sigma Z here, which is in one subsystem, and there is a Z plus X or minus X, doesn't matter, in the other subsystem. Of course, these two observables don't commute, but then they are sitting in different subsystems. Okay? And
Yes, ma'am.
this rule of writing down the expectation this way, right, which is Z plus minus X like this essentially comes from the Born rule, right? The Born rule tells us a way to get probabilities as, this basically this, what is it, trace of the projector size, the projector onto the observable, right? Let's say sigma Z, and then the state, right? So this then becomes psi pz psi, right? And using this Born rule, we define this notion of expectation value, right? But now, if you ask me to trace my steps back, right, and say, this is no doubt just a function of P and R, but can you write down for me a joint distribution for sigma Z A, sigma X A, sigma Z plus minus X B, right? These are the four observables. So can you write down a joint distribution like this such that, what do I mean by a joint distribution? I should be able to take marginals, right? So the question is, does there exist a joint distribution like this? So what I'm trying to say is this expectation value is well defined. Okay, we have a way to compute this expectation value. And if you notice, we are doing it piecemeal. We are doing it separately for P and R and separately for Q and R, right? And the non-commuting observables are sitting in separate systems. So we can compute this expectation value term by term, right? But to constrain the value of M, this M observable, what did we need? We needed to have a joint distribution over which we could sum this entire function, right? So that kind of joint distribution does not exist. So such that the marginal should give me the correct probability distribution for sigma Z, should give me the correct probability distribution for sigma X, should give me the correct probability distribution for Z plus minus X in B. This cannot happen, right? Does there exist such a joint distribution in quantum mechanics where I can have a joint distribution for sigma Z and sigma X on the same system? This cannot happen, right? Such a joint distribution cannot exist. Because it would mean that these marginal probabilities are well defined, right? But they are not. Because if this were possible, then it would mean that I can simultaneously measure X and Z. That's what this would lead to. If I have a way to jointly assign probabilities on the same system, right? Then, because again, you go back, how do you assign probabilities? Through the Born rule. So what it means is I must have, so what are the possibilities, right? If I want to have a ZX joint probability distribution, the possible values are What is the outcome set? It is plus, 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 minus, minus, plus, minus, minus. So I should be able to have a joint distribution over all this. But that cannot be, because you know that I can have a plus outcome here, and then the minus and plus become equally distributed. Similarly, if I have a minus outcome here, the minus and plus become equally distributed for the other observable. So it's not possible for me to simultaneously write down a projector on Z, a projector on X, and a state and define this via a bond rule, right? This kind of thing cannot happen. Is the idea clear now?
Yes, ma'am. Yes, ma'am.
Yeah, so that's the point, that you cannot simultaneously measure these. So you cannot have a joint probability distribution whose marginals will give you the statistics for X and Z, right? Because as we discussed, there is a certain uncertainty relation in play that if I have an X measurement and follow it up with a Z measurement, it completely scrambles the information in the X basis. So I cannot then have a marginal, consistent way of defining a marginal for X and Z. Okay, because that would then imply that I can somehow simultaneously measure X and Z.
Yes.
Yeah. Any other questions? Okay, so I've put up a bunch of references on Moodle, no? So please go take a look. Maybe I'll just mention one last thing before I wind up, that the first experimental test of the Bell-CHSH violation was actually done in 1982. So in some sense, quantum mechanics was experimentally verified in 1982. Famous experiment by Alan Aspey's group. Using, of course, photons. Those are the simplest systems to engineer and do these kind of tabletop experiments. So if you can, I urge you to go look up this paper of Alan Aspey. Right? Although today, yeah, I mean, I've uploaded a recent paper where they show this in nuclear spins and so on. But you can go ahead and read up on your own. Okay, so then I will see you all on Thursday, and we will now shift gears and start talking about what we intended to do, which is quantum gates, circuits, and move on to algorithms soon.
Excuse me, ma'am.
Yeah.
I have a question from last time's lecture.
Yeah.
So last time it was mentioned that the Smith decomposition is unique up to local unitary gate.
Correct. Yeah.
So what what was mentioned there that the basis might change, but that the probability with which I'm preparing my ensemble, that those coefficient, those should not change. They will remain invariant.
The lambdas will remain invariant, because see, the lambdas are nothing but they are coming from a singular value decomposition, right? If I take a bipartite state psi AB with coefficients Cij, right, then that C matrix, you do a singular value decomposition of that will give you the lambdas, right? So yes, those do not change. But you can do local unitaries on subsystem A and subsystem B and rotate to different bases where you may still have the Schmidt form. This is particularly stark when you look at, for example, one of the Bell states, right? And that's what we did last time, right? Where you have the same Schmidt form when you go to a different basis as well, which is a plus minus basis. Right?
Yes.
So but I'm not saying that it is always possible, but I'm saying that it may be possible that you can rotate. There is usually this local unitary freedom which you can use to rotate your local Schmidt basis. Of course, that cannot change the entanglement content of the state. So the lambda i's are something fixed, right? The Schmidt
Yes.
coefficients are invariant. And those are the ones which capture the entanglement content of the state.
Sure. Thank you.
Okay. Okay. See you all on Thursday.